There you go.
Thank you. Good morning. This is the last class on some basic information, background information for refractories. So we covered chemical bonding, we covered crystal structures, we looked at glasses, especially silicate glasses, and we're going to finish up phase diagrams today. So any one of these topics, if you were in college, could be a complete undergraduate or graduate course. So we're giving a very brief introduction so that it you'll have the right background for the different refractory compositions. So when we go over the refractory compositions, each one we'll go over raw materials and we'll follow that by phase diagrams, and then we'll do processing, microstructures, and these are my personal, pretty much all my personal collection of over 30 years of SEM studies of microstructures, and then some of the key properties. So we'll finish up phase diagrams today and start on refractory compositions next week. So we did binary phase diagrams for 2 classes. So the last class is 3 component phase diagrams. And we'll do simple eutectic ternary diagrams, congruent melting ternary diagrams, incongruent melting diagrams, and diagrams with ternary compounds. Some of these diagrams will have polymorphic transformations. There's also immiscible liquids and solid solutions. So we'll go over these basic diagrams. We'll look at some calculations for compositions on the ternary phase diagrams. And then, and more importantly, probably are the crystallization paths. So this is a 3-dimensional model of a very simple eutectic ternary phase diagram. So this base, A, B, and C, is an equilateral triangle. It doesn't look like it here, but they're all 3 sides are equal. And A, B, and C at the corners are the pure components. And then in the vertical direction is temperature. So the vertical axis is temperature. So any compositional point in the center of this triangle is going to contain all 3 components, A, B, and C. But if we look at the sides of the equilateral triangle, any point on this side, AB, is going to only have A and B present. On side BC, any point on that side will only have B and C. And then on this other line, AC, any point on that line will only have components A and C. And then if you go up the temperature axes, TA is the melting temperature of the pure component A. TB is the melting temperature of this pure component B. And in this corner here, TC is the melting temperature of the pure component C. So each side of this ternary phase diagram are really binary phase diagrams. And in this particular model, they're simple binary eutectic diagrams. So this point E2 is the binary eutectic for this side AB. And actually this horizontal line that intersects E2 is a solidus curve. And then E3 is the binary for eutectic in this side BC. And then this horizontal line is the solidus curve. And then E1 is the binary eutectic for the side AC. And this dotted line is the solidus curve. So 3 eutectic diagrams, AB, BC, and CA. So TE1, which goes through E1, is the solidus line, and it's the melting temperature for this binary eutectic on the side AC. And then TE2 is the solidus line for this eutectic E2. So it's the melting temperature for that binary eutectic. E2 is also represents a solidus line. And then TE3 is the melting temperature at E3 for that binary eutectic B and C. So you can see on this side, simple binary eutectic BC, the solidus curve, the liquidus curves, and this would be C plus liquid, this region, this would be B plus liquid, and this would be B and C in the solid form. So looking at the top surface only, the top surface is the liquidus surface in this ternary phase diagram. So all the points above these curves, these surfaces are going to be liquid. So they're all up here as a liquid. You'll see on these liquidus surfaces, these contours, these curved lines, they're lines of constant temperature or isotherms. And then these lines starts out solid here and goes dotted, and this one is dotted, and so is this one. These are the boundary lines between the different liquidus surfaces. So if we look at our phase rule for this three-component phase diagram, we're going to emit pressure. So our phase rule reduces to F, the degrees of freedom, equals the number of components minus the number of phases plus 1. So if we look at the liquid here, we only have one liquid phase. So the degrees of freedom equals 3. C is 3. There's always 3 components, A, B, and C, minus 1 phase, P. So 3 minus 1 plus 1 is 3. So it has 3 degrees of freedom and only one liquid phase. This other point, E, is the eutectic in this ternary phase diagram. It's an invariant point. So there are 4 phases present here, the 3 solid phases, A, B, and C, and then the liquid phase. So F equals 3 minus 4 phases plus 1, or 0. So that's an invariant point, 0 degrees of freedom. If you're on the liquidus surface, you have a solid phase. In this example, it would be C and 1 liquid phase. So P is 2, so F equals 3 minus 2 plus 1, or 2. Says 2 degrees of freedom. And then if you're on the boundary line here, that's a univariant line. You have 2 solid phases, and this line represents A and B, and 1 liquid phase. So 3 phases, so F equals 3 minus 3 plus 1, or F equals 1 degree of freedom. So that's how the phase rule looks on a ternary phase diagram. So a diagram like this is not that useful. What is useful and how all the phase diagrams, the ternary phase diagrams are presented is as a projection. So you transfer the information of this 3-dimensional model to this 2-dimensional model. So you're just projecting the boundary lines and the contours onto this plane. And that's that equilateral triangle, ABC. So this is what you'll see when you look up ternary phase diagrams. Here's the melting temperature of component A, the melting temperature of component B, the melting temperature of component C. Now the boundary lines have these arrows on them. The arrows indicate directions of decreasing temperature. So this is your eutectic in this phase diagram here. That point E is in the center here. So A, region A is the primary phase field for component A. So if you're in this phase field, the composition, you're going to initially crystallize component A. B is the primary phase field for component B. So this is the phase field B. So if you have a composition in B, as you cool it, B is the first to crystallize. And then region C is the primary phase field of this component C. So any composition, initial composition in this region, you'll initially crystallize C. So you can also make isothermal sections. So you can transfer the information from this three-dimensional model to a two-dimensional model by drawing an isothermal section. So this is just a horizontal plane parallel to that equilateral triangle in our three-dimensional model, and it's a horizontal plane of constant temperature. So in our model, this is the isothermal section at temperature T3. So here's temperature T3 over here, and then the isotherms are on the other side over here, T3. So when you take that horizontal cut, you have a liquid region in the center. This is C plus liquid, B plus liquid, A plus liquid, and this is at the eutectic region, A plus B plus liquid. So another isothermal section at temperature T7 on that same diagram. T7 is right here, very close to the eutectic. So right in the middle, we have all liquid, and then this region is C plus liquid, this region is B plus liquid, and then this is A plus liquid. And then we have these other regions, A plus C plus liquid, B plus C plus liquid, and then A plus B plus liquid. So this is the most common presentation, looking at a liquid surface. And in some cases, if somebody does all the work to get the phases present at these different isotherms, you'll see cuts like this as we decrease the temperature. And there's also a third way of presenting this. So we're taking our three-dimensional model, converting it to a two-dimensional model. So instead of a horizontal plane, we draw a vertical plane. So this is a vertical section on a region of the ternary diagram. So here's a vertical cut from A to BC. So this diagram has component A, component B, and then component C. But on this side, there's a compound BC. So we're drawing a vertical section from this compound BC to A. This happens to be an incongruent melting compound. This is actually the phase field for BC. This is the phase field for B. This is the phase field for A. And then this is the phase field for C. BC is outside its phase field, so it is an incongruent melting compound. So here's our binary phase diagram through this cut. BCA looks like this. Here's A, here's BC. And then when BC melts, it goes to a different crystal, C plus a liquid. So there's three ways of presenting these diagrams. This is the most common, just projection of the liquid surface. There's isothermal cuts parallel to the base, and these other cuts vertical to the vertical or perpendicular to the base. So this is a three-dimensional diagram with a congruent melting compound AB. So AB is over here. So here's B, CA, and then this compound AB. It turns out that AB is in the primary phase field of AB, so it's a congruently melting compound. So this is just a simple eutectic binary phase diagram along BC, same thing along CA, simple eutectic. And then this one is a diagram with a compound AB, and it actually has two simple eutectic diagrams if you split it along this line AB up to its melting temperature. So here's your two-dimensional projection. This line ABC is an alchemade line, and it just represents the intersection of the vertical plane with the liquidous surface. So it intersects the boundary line between these eutectics, E1 and E2, and that's the point M where it intersects this boundary line between the lowest melting eutectics, E1 and E2. This line AB to C actually separates this side of the diagram BA into two separate phase diagrams, two simple eutectic phase diagrams with eutectics at E1 and E2. So the temperature is going to decrease along the alchemade lines, and they're going to reach a minimum at N. So this one decreases from AB to M, and then the other side here decreases from C to M. And then as you further decrease the temperature, you're at this low melting point M, but you'll go from M to E2, or M to E1, or M to E2, depending on your composition where it starts. So this line BC is an alchemade line. This line AC is an alchemade line. This line AB is an alchemade line, and so is this one, BAB. They're all alchemade lines. So this is connecting C and A, and it's also the boundary intersects A and C between phase field C and A. So it has to connect the two phase fields. So this one is B and C. This is phase field C and phase field B. It intersects BC. So they're all alchemade lines. But this line from A to B is not an alchemade line because the primary phase fields for A, which is A, and B, which is B, they're not adjacent. They're separated by this other phase field, AB. So there's no common boundary. So it's not an alchemade line. So all compositions in this triangle, B, A, B, C, are going to, when they crystallize, their crystallization path is going to end up at E1. Then all compositions in this triangle, A, B, C, when the crystallization is complete as we lower the temperature, are all going to finish at E2. And then this alchemade line from AB to C, the phase fields A, B, and C are adjacent. It separates the side into basically two ternary phase diagrams. One is B, A, B, C, and the other one is C, A, B, A. So this is the projection for the liquidus curves for an incongruent melting compound. So it's a two-dimensional projection of a ternary phase diagram with an incongruently melting compound, and that's AB3. So here's C, A, and B, and on this side of the diagram, on the AB side, there's a compound AB3. So this is a simple eutectic binary on this side, BC. On the side AB is another simple eutectic binary. But on this side, AB, we have an incongruent melting compound because this compound right here, AB3, is not in its phase field, AB3. So compound AB3 lies outside of its primary phase field, AB3, so we know it's incongruent. And if you look at the binary phase diagram along AB, you can see that AB3 is an incongruently melting compound. AB3 melts to another crystal phase B plus a liquid of a different composition, and that liquid composition is at point P. So on this diagram, this is a ternary eutectic E, and then point P is a ternary peritectic because we have an incongruent melting compound that correspond to this peritectic point P. So all compositions in this triangle, B, AB3, and C, if we start out with a composition within this triangle, their crystallization paths will terminate at this peritectic point P. So C, AB3, and B are the three components. If we start out with any composition in this phase field given by this triangle, so we have C, B, and AB3. So it has to end up with those three compounds. So here's the phase field for C, B, and AB3. So if we start in this compatibility triangle, AB3, B, and C, we have to end up with those three phases, B, C, and AB3, and that's that point P. Now, if we have a composition in this triangle, A, AB3, and C, we have to end up at the eutectic E when we crystallize as we decrease the temperature. So this compatibility triangle is C, A, AB3. We have to end up in those three phase fields, C, A, and AB3, which is this point E. So if we don't have the temperature contours on here, but compositions in this triangle, B, AB3, C, are going to be more refractory than in this triangle. Actually, A, AB3, and C. If you follow the arrows, you see they're in the direction of decreasing temperature. So if you, again, look at the arrows, E is a lower temperature than P. And this region is a much lower temperature than over here. So compositions in this triangle, A, AB3, and C, are going to contain a liquid phase at a lower temperature than in triangles, and in triangle B, AB3, and C. So this is the low temperature region of this phase diagram. So if you start out with compositions in this compatibility triangle, they'll be more refractory than in this other compatibility triangle. This is a ternary compound example, and it's congruently melting. So here's a compound ABC. There's four phase fields. This is A, this is B, and then this is C, and then this is ABC. And the compound chemistry is in the ABC phase field, so it's going to be a congruently melting ternary compound. And again, ABC lies in its own phase field, ABC, so it's congruently melting. Here's another example of a ternary compound that's incongruently melting. So we have, again, A, B, and C, phase field for A, phase field for B, phase field for C. Then the primary phase field for ABC is over here, and the compound is over here. So ABC, the compound lies outside its primary phase field, ABC. So it's an incongruently melting compound. This is an example where we have some polymorphic phase transitions. And this is for SiO2. So we just put in SiO2 at this corner. Then we have B and C, other compounds. And these contours are temperature contours, but they represent the stable temperature regions for each one of the polymorphs. So this is alpha and beta quartz. Alpha and beta quartz have a displacive phase transformation at 573 degrees C. So alpha quartz, beta quartz, the 573 contour. And then this is the transformation from beta quartz to tridymite. This is the 870 degrees C contour. From a thermodynamic standpoint, beta quartz is supposed to transform by a reconstructive phase transformation to tridymite. Thermodynamics says that happens at 870, but the kinetics are so slow. Realistically, 1400 degrees C is where that reconstructive transformation takes place. So beta quartz transforms by a reconstructive transformation to tridymite, but really at temperatures around 1400 degrees C, the kinetics are fast enough for that to happen. And then the other reconstructive phase transformation, tridymite to cristobalite, takes place at 1470 degrees C. So that's another reconstructive transformation. So this diagram shows the polymorphic phase transformations for a material like SiO2. And then here we have some immiscible liquids. Here's a three-dimensional model. Here's your immiscibility region. And then the two-dimensional projection of A, B, and C. Here's your region of two liquids on that ternary phase diagram. And then the other thing we can see on a phase diagram are solid solutions. So this binary phase diagram, AB, if you look at it here, this is a complete solid solution. So A and B dissolve in each other completely. You can see the solid solution region here, where we have solid and liquid. This binary phase diagram, BC, there's limited solid solution. So only a little bit of C dissolves in B here. So in this binary phase diagram, BC, you see the solid solution area right here. It's just a limited amount of C dissolving in B. And then this binary AC, this is the solid solution area. It's limited. So there's a little bit of C dissolving in A in this region right here. So if you look at the two-dimensional projection, it looks like this. This dotted line represents solid solution. So in this region here, you have solid solution of A and B, but you also have a little bit of C, partial solid solutions dissolved in A and B. And point C, there's no solid solutions So A and B do not dissolve in C, but a little bit of C dissolves in B, a little bit of C also dissolves in A, and A and B are complete solid solutions. So this dotted line represents the region where you can have solid solubility. So it's actually a volume. You draw this dotted line from this point A. Well, it goes through this point right here, all the way up to the melting point, and it's connecting down to this region here. So that is a volume. It really represents the volume of this solid solution alpha. If you take an isothermal cut in that diagram at 550 C, the isothermal plane identifies the phases present in each region. So here's some solid solution. It's in solid form. This is solid solution plus C, and then you have a liquid region, C plus liquid, solid solution plus C plus liquid, and then solid solution plus liquid. So that's an isothermal cut through a solid solution phase diagram. So this is A, B, and C, and on the axes now are the percents. So C goes from 0% to 100% C, and then B goes from 0 to 100% B. So if we have a composition X, the percentage of each component is proportional to the length of the perpendicular from each edge to that point X, is that composition X. So we just draw a perpendicular from X to one of these three axes. So opposite A is 20% A. So each one of these lines represents 10%. A simple way is looking at A. This is 0% A along this side, and you move in this direction, you end up with 100% A. So each of these is 10% increments going from 0 to 100. So this is simply 20% A. This is opposite C. So it's 1, 2, 3, 4 units. That's 40% C. And then B is also 10, 20, 30, 40. So B is 40%. That's a very simple way to figure out the percentages of any point on this ternary phase diagram. Another way to look at it is you can draw parallel lines through the composition of interest. So here's another point, Y. You just draw lines through Y parallel to all three sides, BC, BA, and AC. And then you can take any one of these sides, it doesn't matter. But this is the side BC. And then you split it up where these lines intersect. So this region is 1, 2, 3, or 30%, 3 units of 10% each, 30%. That's the percent of B. It's opposite B. And then the percent of C, which is opposite C, is 10, 20, 30, 40, 50, 60. So 60% C. And then this small section A is opposite A. That's 10% A. Or you could simply go 10% in this direction for A, or 30% in this direction for B, or C, it's 60%, 10, 20, 30, 40, 50, 60, and you end up with Y. So two different ways of looking at the percentages of the three components at any particular composition in the ternary phase diagram. So we'll look at some crystallization paths to finish up today. This is probably the most important part of the phase diagrams, is to see how they crystallize. This is a eutectic ternary phase diagram. So AB, BC, and AC are all ternary phase diagrams with a simple eutectic. So we'll look at the crystallization path of this composition X, which is in the phase field C, as it is cooled. And on this region in the primary phase field C are the temperature isotherms, T1 being the highest temperature, T7 is this temperature near the eutectic. So from T1 to T7, we're going down in temperature. The eutectic would have a temperature lower than T7. So this composition happens to be 20% A, 10% B, and 70% C. So point X corresponds to this temperature isotherm T3. So that temperature is T3. So above that temperature, T3, everything is liquid. So at point X above temperature T3, we have a liquid phase. So we go slightly below T3, and we're in the primary phase field of C. So C has to be the first phase to crystallize out. And that's because point X here, that composition, is in this primary phase field C. So we drop the temperature from T3 to T4, and that's this isotherm right here. So more of component C crystallizes when we go from T3 to T4. And then the composition of the liquid now corresponds to this point. We're drawing a line from C through X. And that's actually the crystallization path. We'll get to that in a minute, but now we're at 4' on isotherm T4. So that's the liquid composition on the liquid surface, and that's now about 23% A, 11% B, and about 65% C. So the percent liquid and solid at T4, we can calculate that. We draw a tie line from C through X to this isotherm T4 at 4'. So the percent liquid is this CX, that portion of the tie line, divided by C 4'. And these are in the same percentage units as along the sides. So if you look at the percent, CX is 32%, C4' is 37%. So there's about 86% liquid present at that point. The percent solid is X to 4', that segment over C 4', or 5 over 37%, is about 13% solid. So we're crystallizing along this tie line. So we drop the temperature now down to this isotherm T6. And now the liquid composition is given by 6'. And that's about 32% A, 15% B, and 53% C. That's that point right there. So the percent liquid and solid, as we reach this boundary line between the primary crystallization field C and then the primary crystallization field of A, that's 6'. So now our tie line goes from C to 6'. So from CX, that portion, over C 6', that's right here, that's the percent liquid, or 32% over 51. So now there's about 62% liquid. And then from X to 6', that segment over the entire tie line, C 6', is 19/51 or 37% solid. So now at T6, which goes through 6 prime, at T6, the boundary line from E1 to E is between phase fields of component C, its phase field, and component A. So as the temperature decreases below this temperature isotherm T6, the crystallization path now follows the boundary line from E1 all the way down to E. So it goes from E1 to E, but we're at composition 6 prime, so we're crystallizing along this path. So we started out at point X, we draw a line from C through X that hits 6 prime. So we start crystallizing from X along this line to 6 prime, and then we continue to crystallize down to the eutectic. So as we crystallize from 6 prime to E, we're crystallizing both C and A at the same time. And there's no arrow on here, but this is the direction of decreasing temperature from E1 to capital E, the eutectic. So we'll pick a point on this boundary line, 7 prime. So the composition at this point, we just read it off the phase diagram, is about 29% A, 21% B, and 50% C. That's the composition of the liquid at 7 prime. And if we wanted to look at the percent liquid and solid at this point, the percent liquid, we have to draw another tie line from 7 prime through X, and it intersects A and C at what we call 7 double prime. So this segment, 7 double prime X over 7 double prime 7 single prime is 18/40 or 45% liquid. And then the percent solid would be X 7 prime over the whole length, 7 double prime, 7 prime, or 22/40 or 55% solid. And then if we wanted to determine the percent solid fractions at 7 prime for A and C, we have to go along this side, A and C. So percent A is this segment, 7 double prime C over the whole side, CA, and that's 13%. And then percent C is 7 prime, 7 double prime A over the entire length CA, and that's 87%. So we have a liquid of 45%, the solid percentage is 55%, but of that 55%, 13% is A, and then 87% is C. And then we get down to the eutectic region here. And now component B starts to crystallize at E also. So now we have 3 solids, A, B, and C, and a liquid are all in equilibrium. So at temperature just above this eutectic, we'll call it E plus. That composition right there is 25% A, 30% B, and 45% C. That's the liquid composition. And then we can do the percent liquid and solid at a point just above the eutectic. So we have to draw another line from E through X that intersects AC at 8 double prime. So the percent liquid is 8 double prime X, that segment over the entire segment, 8 double prime E, or 33%. And then the percent solid is X E over the entire length. That's 8 double prime E, or about 66%. And if we wanted to see the percentages of A and C solid at that point, we have to go back to this side of the phase diagram, AC. So the percent A is 8 double prime C, that segment over the entire side, CA, and that's about 19% A. And then the percent C is 8 double prime A over the entire side, AC, or about 81% C. So that's what's happening just above the eutectic, the composition of the liquid, the percent solid in liquid, and then the solid fractions, A and C. And the last thing we do, we can look at a point E minus, just slightly below the eutectic. So that eutectic composition is the same as the liquid composition on this previous slide. 25% A, 30% B, and 45% C. So that eutectic crystallizes to this composition. So at a temperature E minus, just below E, it's all solid. The liquid phase has completely disappeared. So the percent solid fractions at E minus, we have a eutectic composition given by these percentages of A, B, and C. So that's 8 double prime over X over the entire length, 8 double prime E. So the eutectic composition, which crystallizes at 25% A, 30% B, and 45% C, is about 33%. And then the solid that crystallizes out, that's A and C, is XE over E, 8 double prime, or about 66%. And then the solid fractions of this portion here, percents A and C, are given on this side of the phase diagram. So the percent A is 8 double prime C over CA, or about 19%. And the percent solid C is 8 double prime A over CA, or about 81%. So that's a complete description of a crystallization of this composition X in phase field C, as it follows this crystallization path from X to 6' to E. So you can get a lot of this information off of these phase diagrams if you go through all those lever rule calculations. So we'll just look at a couple crystallization paths without doing the calculations. This is a ternary phase diagram, A, B, C. It has two eutectics. If we look at the binary phase diagram, here's a eutectic here and a eutectic here, but the ternary eutectics are E and D. There's an intermediate compound, AB. AB is in its own crystallization field. So here's the crystallization field for A. The field for C looks like this up here. B is over here, then AB is over here. So AB lies in its primary crystallization field, so it's congruently melting. So there's an alkymate line between C and AB. So let's look at our composition X and see what happens when we cool it. So X is in the primary phase field C, so we know C is going to crystallize out first, but it's in the compatibility triangle C, AB, and B. So we draw a line. It's in the phase field C, so C crystallizes out first from C through X, and it intersects this boundary line. So C crystallizes out first. It follows this path from X till it hits this boundary line FE. And then it follows the boundary line in the direction of lowest temperature. The arrows are pointing this way to this eutectic. So it crystallizes along this boundary line. So C is crystallizing, and then AB starts to crystallize as we go down towards the eutectic. And then finally, we hit the eutectic, and B crystallizes third. So we start out in this compatibility triangle, AB, B, and C. So we have to end up with those three phases. So that's AB, go back one, AB, B, and C. So that's that eutectic. So we're in this compatibility triangle, C, B, AB. We know we have to end up with those three phases, C, A, B, and B. So we know we have to end up at this eutectic. So C crystallizes first, AB second, and then finally B. Same phase diagram, but now we moved our composition to Y. We have our same alchemade line, CAB, and then composition Y is now in the primary phase field of AB. So AB is going to crystallize out first, but it's in the compatibility triangle C, AB, and A. So we have to end up with those three phases when we complete the crystallization. So that's C, A, and AB. We know we're going to end up at point D, that eutectic. So we draw a line from AB because we're in the primary phase field of AB through Y, and that intersects this boundary. So AB crystallizes out first from Y to this boundary. And then we follow this boundary line in the direction of arrow, lowest temperature. C crystallizes out next. And when we get to eutectic, the third phase, A crystallizes out. So we're in the primary phase field of A, B, C. So we have to end up at this point where those three phases exist, C, A, and AB, and that's point D. So this is another example. We have an intermediate compound, AB, and we'll look at a point X of this composition and trace the crystallization path. Our alchemade line is CAB. Now, this compound AB is outside of its primary crystallization field AB. So we have a primary field for A, a primary field for C, primary field for B, and then the primary field for AB, and it's incongruently melting because its composition is outside of its primary phase field. So this composition X is in phase field B, so B will crystallize out first, but it's in the compatibility triangle C, AB, B. So we know we're going to end up with those three phases, C, A, B, and B. So here's the primary phase field of C, the primary phase field of B, and the primary phase field of AB. So we're going to end up at this point P, which is a peritectic. So we start out drawing our line from B through X. So along this solid portion here, as we decrease the temperature, B crystallizes out first. We hit this boundary line, then follow it down to the peritectic point in lower temperature direction according to the arrows. C is crystallizing out with B as we go down here. And then A crystallizes out, AB crystallizes out third. So now we end right here with crystals of B, C, and AB at this point P, and it stops. It doesn't continue to this eutectic because we're in this phase field A, B, B, and C, we have to end up at this point, P. So this is the same diagram, but I moved the initial composition to Y. So Y is still in the primary phase field of B, but now it's in a different compatibility triangle, C, A, AB. This triangle instead of this one, which we just looked at, B, C, AB. CB, CAB is our alchemade line. And again, AB is outside of the phase field of AB, is crystallization field. So we're in this compatibility triangle C, A, B, and A. So we have to end up at this point E. So here's our phase field for C, our phase field for A, and AB. So we're going to end up over here. So we're in the primary phase field of B. So we draw an arrow from B through Y till we reach this boundary line. So from Y to reach this boundary line, as we decrease the temperature, B crystallizes out first. And then we follow the temperature contour down to point P. C is crystallizing out now along with B. And then we follow this down to the eutectic E. So as we go down here, AB starts to crystallize, but we're no longer bordering the phase field B, so B disappears. And then we continue down to point E, and then finally A crystallizes. So at point E, we have crystals of C, A, and AB, and the B crystals that first formed are no longer, they're gone. So I just moved Y from up here to down here. So composition Y is in the phase field, still in the phase field B, and it's still in this compatibility triangle C, A, B, A. And our alchemade line is still C, A, B. And again, AB is outside the primary crystallization, its primary crystallization field AB. So we're down here in a different part of the phase diagram, but we're still in the compatibility triangle A, B, C, and A. So we're going to have to end up at this point in E with the three phase fields, C, A, and AB. So we'll have to end up at E again. So we're in the primary phase field of B. We start out with B. We draw a line through Y, and we hit this boundary line between A, B, and B. So this little portion of the line is where B crystallizes out first. And then we start moving in this direction along this arrow lowest temperature direction towards point P, but we don't get to point P because when AB crystallizes out, we now have to draw a line from AB through Y, and that intersects this boundary between A and B at this point here. And then the crystallization path follows this arrow instead of the boundary line. So AB crystallizes out second along with B. And as we leave this boundary line, we're still crystallizing out AB, but B disappears. Then we hit this other boundary line between C and AB, and C crystallizes out third, and finally we get to the eutectic, and then A crystallizes out. So we end up with crystals of A, C, and AB at the eutectic. Just a little bit different path here, depending on where we put the initial composition. And I have a few more examples. This is a phase diagram with this compound ABC. So we have a ternary compound ABC. Its phase field is right here. Its composition is outside the phase field, so it's over here, ABC. So it's an incongruently melting ternary compound. And there's 2 points on here, X and Y. So we'll look at X first. So X is in the phase field of C, the primary phase field. And its primary phase field is right here for C. A's primary phase field is over here. B's is over here. And then ABC is over here. So we draw an arrow from C through X, and we intersect this boundary between C and A phase field. So C is crystallizing out first, and then we follow the arrows. We move in this direction. A is now crystallizing out because we're in the A phase field, and we finally end up at this point, P1, this peritectic point. There's 2 peritectic points, P1 and P2, and a eutectic point, E. And then ABC crystallizes out first. So we start out in the compatibility triangle, C, ABC, and A. So we have to end up with C, A, and ABC. So at this point, we have C over here, A over here, and ABC. We have to end up with this point where we have all those 3 phases come together, and that's P1. And then the other crystallization path is for Y. Y is in the B phase field, which is over here. So we start out with a line from B through Y, and that intersects this boundary between A and B. So B crystallizes out first, then A starts to crystallize. And we follow the line down to P2, but we're in the primary phase field of B, A, B, C, and C. So we know we're going to end up at this eutectic E, because that's the point that has C, B, and ABC. All those 3 phase fields come together at E. So we're at P2. We follow this curve towards E. So ABC now starts to crystallize. And then we reach the eutectic E, and C crystallizes as the 4th phase crystallizing out. But as we travel along this path, we're no longer in this phase field A, so A disappears. So B crystallizes out first, A crystallizes out second, then ABC starts to crystallize. Finally, C crystallizes last, and then A is disappearing. So that's the last slide I have. 3-phase diagrams, and I try to show a bunch of different crystallization paths. So when you see a 3-phase diagram in some of our refractory compositions, you can figure out how the material crystallizes, and they'll have temperature contours, and you can see their use temperatures from those temperature contours. So you can see where the liquid starts to form, and you can predict where you can use these materials, what temperatures you can use these materials, and what phases will appear. So one other note, these we did binary and ternary phase diagrams. Refractory compositions tend to be more complex. They're going to have impurities, and the impurities are going to be in smaller concentrations, and they're going to change the properties. So what you have available nowadays are computer calculations based on thermodynamic data. So if you have a complicated system, say you have 10 different compounds present, and you can put in those compounds at a particular temperature, and these programs will calculate the percentage of the phases present and the amount of liquid present. So very complex refractory systems, especially systems in contact with a glass or a slag. You can do these calculations quite simply, and you can see what your solid phases are, how much liquid is there. So you can predict what happens to these refractories as you heat them up, or as you heat them up in contact with other chemicals. So that's very useful for corrosion studies and very useful for looking at high temperature properties like strength. So that's where we'll stop today. Next week, we'll start the refractory compositions with silica, and then we'll add alumina for all the alumina silica refractories. So have a good weekend, and thanks for listening in, and I'll see you next Monday. Thanks again.